right. Looks like all the sound is working. All right. Euclid. So when I play tennis, I also think that the arm is like shoulder, elbow, wrist. These are also like compass. You know, it's just very much, I can think of my arm when playing tennis. It's like a 3-point compass, as well as other dynamics of how swinging a tennis racket works. It's like this. I mean, usually you use your shoulder more with the tennis, but then you also get, you know, the elbow in there. That's another rotation point, and then the wrist is another rotation point, and the fingers can also put more interesting motion into that tennis racket. And it's also how you move your body and how you connect the momentum of your body to that momentum of the racket at the point you hit the ball. It's very very much compasses and straight edge, and that straight edge is that tennis racket. Okay, so let's do a little more math practice here. It's kind of, I would say, not that practical if all that you think you can use in this universe is a compass and a straight edge. Like, you can't even use these measurements for the ancient Greeks, especially I think Euclid came up with all this stuff. But it's just so interesting, just pretending you cannot use measurements. All you have is a straight thing and a compass. Maybe I should use something else besides these cool diesel things. Alright, I'll just say, just using this part of the straight edges that do not have measurements on them. Use this part and this part. Okay. It's a great video by Mythologer again. Alright.
Welcome to another Mythologer video. Today's video is one I've been dreaming about making for a long time. Today I'd like to dazzle you with the solutions of some of the most famous problems in the history of mathematics. These problems had remained unsolved for more than 2,000 years after they were first puzzled over in ancient Greece. The problems arose very naturally as part of the Greek mathematicians' quest to determine the possible geometric constructions when all we're permitted is to draw lines and circles. That is, what is possible using just the most basic mathematical tools, the ruler and the compass. For example, given a square, we could construct a new square of twice the area just using our basic tool.
So, just getting used to these rules.
However, unlike doubling a square like this, doubling a cube turned out to be anything but easy. Nobody was able to figure out whether, given a cube, we could construct a cube of double the volume by just using ruler and compass. This is the first of those ancient problems I'll be tackling today. Similarly, if you're given two lines making some angle, then halving that angle with ruler and compass is easy. There, just draw a couple of circles there.
I want to do this. Okay, you have an angle. Okay. Huh. What is going on there? Another circle, another circle. And this. Huh. Just complete these circles, be clear. Hmm. Gotta get used to using these. And that's a circle. These all look like congruent circles. That's a circle. Man. There's this. Just looking at that. It's kind of. This is a circle. This is how you bisect an angle. Very interesting. almost hits that point, but does not hit that point. Oh man, not using this well. Basically, right. Put this thing here. All right. This is the point. Whew. I'm learning to have eyes for this geometry. So that thing is gonna bisect the angle. Yeah. This thing.
And there is the bisect.
Cause yeah, man. You know, in my crude eyes for geometry, this circle looks like it could almost hit this point and almost hit that point. And there must be very, very precise measurements of what is this difference. And anyway, this is the bisector. All right, that's the bisector. Wow. Okay.
But nobody could come up with a ruler and compass construction that would trisect an arbitrary angle. That's problem number 2. Next, using ruler and compass to construct equilateral triangles.
All right, wait. I didn't really do the first one here. What was the first one?
We could construct a new square of twice the area.
Huh.
Using just the most basic mathematical tools, the ruler and the compass. For example, given a square, we could construct a new square of twice the area just using
Twice the area. Twice. Okay. Square. Square. Alright. It's freaking 20. That's 1 square. I get twice the area by call this 1. We call this 2. So yeah, because 2, that would be 2. So yeah, if you say this is length 1, length 1, this diagonal, oh man, diagonal, magical math technique of George Cantor. Anyway, I'm not going to say too much about that. And then so that square, yeah, would be 2. This is area 1, this area 2. But I mean, having, yeah, I mean, use a compass like this. Oh shoot, this is kind of small. Basically, square is too small for this thing, I think, maybe. Wait. Oh my gosh. That is kind of a sorry circle. But yeah, go this, and just connect. Basically, that's what he's showing, right?
Or basic tools. However, unlike doubling a square like this, doubling a cube turned out to be anything but easy. Nobody was able to figure out whether, given a cube, we could construct a cube of double the volume by just using ruler halving that angle construction that would regular pentagons intersect an arbitrary angle. That's problem number 2. Next, using ruler and compass to construct equilateral triangles, squares, regular pentagons, and regular hexagons is not a problem at all. But what about regular heptagons? Nobody had a clue for thousands of years. That's problem number 3. Finally, most famously, and what turned out to be by far the hardest, is it possible to square a circle? That is, given a circle, is it possible to use ruler and compass to construct a square of exactly the same area? Well, as I said, it took over 2,000 years to finally answer these questions. And what's the answer? The answer is, stop trying, you're wasting your time. In the 19th century, it was proved that it's impossible to use ruler and compass to double a cube, or to trisect an arbitrary angle, or to construct a regular heptagon, or to square a circle. But who gets to see these impossibility proofs? Not many people, except a few pure maths majors who may encounter them immersed in a course on Galois theory. Really heavy-duty stuff. However, on close inspection, it turns out that those proofs only really require some of the semi-heavy-duty parts of Galois theory. Then, if you are incredibly stubborn, and you try really, really hard, it's possibly possible to distill the essence of these proofs into one short and not too hard YouTube video.
Short.
I don't know about you, but I find the idea of making a video like this super exciting. It's an opportunity to make a small but tangible contribution to something that people have been struggling with for thousands of years. And I hope that for you, it's an opportunity to get to the core of some classic and beautiful and hard mathematics, to get some insight into a theory normally considered out of reach of mere mortals. Okay, here's the plan for today.
Okay. So this is what really caught my eye. I'm like, somebody found this. This is not easy, and I need to practice, especially the compass part. My techniques are very laughable, but I want to be able to do this, construct this pentagon like that. That seems damned complicated, and the fact that someone came up with this, probably Euclid, is just so great. Alright. So interesting what this is. It's the Sphex Mini by Razer. Maybe in a future YouTube video I'll explain why Razer Naga is so closely associated with diagonalization and Cantor's diagonal technique. I don't know, something in my wild imagination is just really putting this Razer Naga to, or just Razer, the story of Naga Sadao, one of the Sith Lord heroes of his people, and how he I don't know. This is all fiction. I don't know why I spent so much time thinking about Nagasadao and fiction. But something about him and bishops on a chessboard. That diagonal bishop. Anyway, all these, I guess, more interesting tangents than what people would find this to be that interesting. But alright, I'm just gonna try to improve my techniques a little bit here and play some more Halo after. Don't have too much time. Alright. Basically, what the heck is this? 1, 2, it's like 3, 4, math. Okay, pentagon from that. Oh my goodness. Shoot. 1 circle, 2 circles. So where does he start with this? Okay. Basically, 1 circle, 2 circles, 3 circles. Okay, I guess we just have this image. Have to deduce the order of operations here. Which circle does he begin with? This is funny. I think he should notate something, because it's I guess this is the fun of math. Basically, I mean, I might not get this tonight, and I want to play Halo, so just kind of meditate on what is the order of operations here. Where's the first circle? Where's the second circle? Am I supposed to be thinking bigger circles to smaller circles, or smaller circles to bigger circles? So, circle, circle, circle. 1, 2, 3, 4. I count how many circles? 1, 2, 3, 4 circles maybe. This thing. 1, 2, 3, 4. What's he doing here? 1, 2, 3, 4. Draw 1 circle. This circle looks bigger than that circle. Oh man. One circle. Alright. I think I want to play Halo more than I want to deduce this thing that does not have an order of operations. Anyway, I will Sith Jedi meditate on this thing, see if I can understand this at some point spontaneously, or maybe I'll try to look up somewhere else that has an order of operations. It'll be probably a lot easier. Anyway, that's it for this math practice. Just to make this bigger, so I'm trying to concentrate on what is the order of operations here. Woo!